this clip we are going to estimate a vector autoregressive model for a system of 3 series here. The data we have in this EVIEWS file are the French, the German and the US long-term government interest rates. So let's firstly have a look at these. You should always have a look at the data. So we open all of the 3 series as a group, and you can see these are interest rates expressed in percentage points. And let's have a quick look at the data. We'll have a line graph, we have multiple series, but we'll put them in one graph. And here you can see the series, and what you can see is that they generally move together, especially in the latter part of the series. In the 80s there was a period where they didn't move that closely together, although the general tendency still matched more or less. So what we are now going to do is to estimate a simple VAR1 model for all of the series. We can delete this graph, delete the group. Yes, so we have our 3 series highlighted, and what we now going to do is we're going to highlight the US, and the ordering will matter very soon. So we're going to do the ordering US, Germany, France, and we open this as a VAR. So here we can specify the VAR. We have our 3 series here, so we'll firstly have a quick look at the VAR in levels, although we know they are non-stationary, we possibly shouldn't do that. And we do a VAR with 1 lag. So what we do is the first lag is 1, the last lag is 1, so that's a VAR 1, and we have a constant, and we click OK, and we get some VAR. And you can see already that the lag for the US long rate, the 1 period lag for the US long rate, the own lag, is very close to 1. It's the same for the Germany and for the French series. So that possibly indicates that's a possible indication that we have non-stationarity here. So what we are going to do is we will want to estimate this for stationary series, so the first differences, and it's very easy. You just put a D and then parentheses around your series, okay? And that will tell EVIEWS that you want to actually use the first differences. You could of course also first create the series and give them new names, the different series, and then apply the VAR to these series. So we press OK. You see we get very, very different coefficients. Now since let's see how many coefficients we have. We have 3 variables, that means we get 3 columns, 1 for the coefficients in the US equation, 1 for the coefficients in the Germany equation, and 1 for the coefficients in the France equation. In each equation we have, let's see, 4 coefficients. We have the constant down here in the bottom, and then we have the 1 period lags in the US equation, 1 period lag, the own lag, the US lag, 1 period German lag, 1 period French lag. Okay, and we have the same for the Germany equation and for the French equation. Let's have a look at which coefficients are significant. Let's firstly see what information we are given. In parentheses we have standard errors, in square brackets we have the t-stats, so we'll look at the t-stats. And we'll firstly see that the coefficient to the 1 period US lag is significant certainly in the US equation, certainly in the Germany equation, and certainly in the France equation, all with very significant t-stats, way larger than 2. So the 1 period lagged change in the US long-term rate has an influence on this period's changes in all. No, that wasn't meant to be there. Has an influence in this period's changes in all 3 equations. Now let's look at the 1 period German lag. Turns out this is only significant in the Germany equation. Okay, so the change in the German long rate from one period ago only has an influence on this period's rate change in Germany, and last period's French change in the long rate interest rate is not significant anywhere. Okay, so we don't actually need that last element to explain the variation in today's changes in the long rates. What we shall do next is to establish whether the fact that we used VAR 1, so one lag in the vector autoregression model, whether that was sufficient to basically capture the dynamics in the changes of our interest rates. The way to do that is to do a test on the residual autocorrelation. If that one lag is sufficient, then we should find that the residuals aren't autocorrelated anymore. So the one lag of the changes in the long rates capture all the dynamics. So we'll go to View, Residual Tests, Autocorrelation LM Test, and let's use lags of 2. So what we get here is 2 tests. This first test tells us whether the first order autocorrelation is significant, and this test tells us whether the second order autocorrelation is significant. So what we see is basically that both we have p-values tiny or very close to 0, certainly smaller than any of our usual significance levels. So that means that there is certainly first and second order autocorrelation in the residuals of the VAR 1 model. That means the VAR 1 model by itself isn't sufficient to capture all the dynamics. So now that we've established that a VAR 1 is most likely not sufficient to model the dynamics, what we shall do now is to see whether we can find out what lag order we should use. So we go to View, Lag Structure, and we go to Lag Length Criteria. And let's select 4. We'll let EVIEWS choose between VAR models up to order 4. And this is the table we get. Okay, so it's the table with our information criteria. And let's see what we can find here. We have all sorts of different criteria here. Let's only look at the Akaike and the Schwarz criterion. These are the ones we are familiar with. And we can see that the Akaike criterion selects a lag order of 3. Okay, that's where we can find the asterisk. It's the smallest value of that particular information criterion. And the Schwarz information criterion selects a lag of 1. Now between these two, which ones would we choose? Well, we've already rejected a lag order of 1 because we looked at the residual autocorrelation and decided, well, there clearly is leftover residual autocorrelation. So that by itself would let us decide, possibly go for a lag order of 3 here. So let's estimate a VAR 3. Go back to the estimation. We change our maximum lag from 1 to 3. Everything else remains unchanged. We estimate the model. So here we go. Now we have for each equation, we have 9 lag coefficients and 1 constant. So for each equation, we'll have 10 coefficients. Let's not look at the coefficients themselves too much. You can still see that the first set of coefficients relates to lags of the US, of the changes in the US long rate, and they are still, the first lag is still significant for all 3 equations. The second lag is significant for the US equation, and we could look at that in detail. What I now want to look at is whether there's any issues about the non-stationarity of the system or the stability of the system. What we'll do is we'll go to View, and we shall go to the lag structure and to the AR. That's starting to be a bit annoying. And lag structure and to the AR roots table. Okay, and what we see here is all the roots of our system. And what we are looking at here is the absolute value. We may have complex roots. What we are interested in is the modulus, which is sort of the absolute value of a complex root. They are all smaller than 1, all inside the unit circle. That means this system is stationary. So there's no problem with non-stationarity. Of course, you could try yourself and estimate that VAR model on the levels, not on the changes of the interest rates, and you would find a different picture. So, of course, now that you have chosen a VAR 3, you could check the residual autocorrelation again, and you would hope that most of that is captured and has by the 3 lags included in the VAR. So hoping that there's no residual autocorrelation, I leave that up for you to test yourself. Now what we're now going to do is we're going to move to the interpretation of this VAR system, and you will have learned that the main tool to do this is to use impulse response functions. Okay, so how do we do that? In EVIEWS there's a little button called impulse. That sounds alright. So we'll click on this. Now there's a number of things you need to do on Node. Firstly, let's not use standard errors. That just makes the graphs cluttered. You can switch on the option and see what happens. You get standard errors for the impulse response functions. We'll choose none. Now if you go to impulse definition, this is where all the magic happens. You will have learned that what we usually do is the Cholesky decomposition, and what is important is in which way we order that decomposition. Here we'll order it from US first to Germany, then France. Okay, even if little Anton doesn't like it. Cholesky ordering US, Germany, France. Let's let EVIEWS do its magic, and here we got our impulse response functions. Let's have a look at this. So what you can see here, one thing I don't quite like about these impulse response functions in EVIEWS is the labeling of the x-axis. It would be better if it's at 0, 1, 2, 3, 4, 5 and so forth, but hey, it does most of the work for us. We're not going to complain. So you can see there are some impulse response functions that are characteristically different, have very different characteristics. Some have non-zero values right from the start in lag 0, which is labeled 1 here. Others start at 0, like this one, and this one. Now it turns out these 0 values for the immediate or contemporaneous responses to shocks are imposed by the Cholesky decomposition, by the particular ordering. So let's look at that in detail. What we have is, in the first row, we have the responses of the change in the US long rate to first shocks in the change of the US long rate, then shocks in the change of the German long rate, and then shocks in the change of the French long rate. The second row will give us the responses of the change in the German rate, first to shocks in the change of the US rate, then to shocks in the change of the German rate, and then to shocks in the change of the French rate. And the last row gives us all the impulse responses for the French rate, or for the changes in the French rate, first to shocks in the changes of the US rate, then to shocks in the changes of the German rate, and then to shocks in the changes of the French rate. So we ordered US, Germany, France. What that implied is that we ruled out that the US rate, or the change in the US rate, would be contemporaneously affected by shocks to the German or the French rate, and therefore this graph, and I didn't want to click on this graph and this graph we forced to start at 0. Then the second country was Germany. That meant that we ruled out that changes in the German rate would instantaneously or contemporaneously be affected by shocks to changes in French rate. And this is why this graph starts at 0. Okay, so this is what the Cholesky decomposition imposed, that we start at 0. The rate afterwards, the impulses can become non-zero. So what do we see? In the first column, we see the responses of the 3 series to shocks in the US rate, and we see that all of them respond positively. Okay, so immediately, if there's a shock in the US rate, the changes to the US rate, this will of course have an immediate effect to the US rate by definition, but it will also have an immediate effect on the German and the French rate. What about shocks to the German rate? We said this was ruled out to have an immediate effect, and even subsequently shocks to the German rate don't seem to move the US rate. Okay, it just stays basically at 0. Of course, we have an immediate effect by the German rate, and indeed the French rate seems to react to German rates changes as well, or shocks in the changes to the German rate. Now, shocks to changes in the French rate, really, they stay in France. Neither the US nor Germany seem to react to those. So you would have learned that the ordering of the Cholesky decomposition is quite crucial, and of course you saw that here already because we enforced these 0 starts for the impulse response functions according to the ordering. So let's go back to the specification and let's change the ordering. So we'll leave Germany in the center, but we exchange the US and France. So US will be last and France will be first. Now we click OK, and we can see that we get quite some change. Firstly, let's see what we have imposed with this Cholesky decomposition. We still have in the first row we have the US equation, second row Germany equation, third row France equation, first column responses to US shocks, second column responses to Germany shocks, and third column responses to French shocks. Now what you can see is we previously had both Germany and France immediately, instantaneously responding to US shocks. This has now been ruled out because the US has been ordered last. That means we now have 0 immediate effects of shocks to the US changes in the long rate to the German and the French equivalents. However, and that is different to the previous ordering we had, now you can see a noticeable increase of the impulse response functions after the first period. Okay, so after one period, here level 2, you can see that there is some positive response now to US shocks both in Germany and France. Now what you can also see is, now that we changed the order, we can now see that, for instance, the response of Germany to shocks in France, we are looking at this graph, second row, third column. Now there's a noticeable positive response of the German market to shocks in the French market. We didn't see that before, although it wasn't imposed to be equal to 0. Okay, so that is clearly another difference we can see. So without doubt, the ordering is very, very important, and you need to think a little bit about which one makes sense. And I think, given the importance of the US, the German and the French market, it's possibly the first ordering which we used, which makes somewhat more sense than this ordering. Let's go back to impulse response, and what we shall use now, instead of the Cholesky decomposition, we now use as decomposition method the residual decomposition method. Now what that means is you can see the ordering is disabled. We don't need that anymore. This implicitly assumes that there is no contemporaneous correlation between the residuals. So the impulse response functions which we will see very soon, as soon as we click OK, will be correct if that's true. However, they will be seriously misleading if there is contemporaneous correlation between the residuals in the three equations. So let's click OK. And what you can now see is that basically the following. Firstly, you can see that we have clearly positive effects in the own countries. So in the US to shocks in the US, in Germany to shocks in Germany, and to France to shocks in France. That's not surprising. And you can see that all off-diagonal impulse response functions start at 0. And of course that is imposed because we said we assume there is no contemporaneous correlation. There's no correlation between the residuals, so by definition there's no response of the German market to shocks in the US contemporaneously, because remember, the VAR itself will only respond one period after, because we're having the 1 period lags, the 2 period lags, and the 3 period lags. So contemporaneous shocks can only come through the residuals. And we root out any correlation, so therefore all these off-diagonal impulse response functions will be 0, and in general they'll all seem to be very small. If at all, we can see somewhat positive responses to US shocks again. So it looks very much, these ones look very much like the Cholesky decomposition, the second one we had, but there's other changes here. So this is all I had to cover in this clip.